Hey there, my name is Gary Sims and this is Gary Explains, and this is my second video on RISC-V. As I said in the first video, I have 40 minutes of material and I thought that was too long for one big long video, so I've divided it up into 4. This video is about what goes into designing a processor in terms of the microarchitecture design, in terms of the plumbing, in terms of the manufacturing, in terms of the software that you get when you design a RISC-V processor. Okay, so if you want to find out more about designing a RISC-V processor, please let me explain. Now, I wanted to talk a bit about what does it mean to design a processor, because some people seem to be a little confused about how difficult it is to design a processor. Now, we've talked about the instruction set architecture, and we'll talk more about that in a moment, but RISC-V is an instruction set architecture, just as ARM, V6, V7, V8 are instruction set architecture, just as Intel's x86, AMD's x86 with its x86-64, these are all instruction set architectures. What do those ones and zeros mean, and how do they interact with each other? But then there's also the microarchitecture, we'll talk about that, the plumbing, what else goes into a processor, the manufacturing, and then once you physically got the chip in your hand, what can you run on it? So let's look at those. So starting at the microarchitecture, if you look at, let's say, Intel, for example, here are some of these code names that you may know: Skylake, Kaby Lake, Coffee Lake. Okay, and these are the different generations of the processor. So the Skylake was the 6th generation, i3, i5, i7, Kaby Lake was the 7th generation, and so on. Now, each of these chips have the same ISA. They all follow the same basic instructions that are compatible on Intel's chips. But the point is that these actual designs, okay, every year, every 2 years, whatever Intel are doing, they release a new design that's the same compatible. If I had a 6th generation i3 processor and I have a 7th generation, well, I can install Windows on it, I can install Linux on it, I can install whatever on it, because it's still compatible with previous generations. But Intel spent a lot of time, a lot of money making each of these new generations, and each of these new generations does two things. One is it supports a new fabrication process, so we might go down from 14 nanometers to 10 nanometers or whatever, but also it's a new interior design, the microarchitecture, how it is built, so they can get more efficiency out of it and they can get more performance out of it. And it's the same with AMD. We had the K8, which was the Athlon 64, the first processor with a kind of the x86-64 in it. Then after that we've had the Bulldozer, then we've had Zen, and then we've had Zen 2. Okay, and these are the different designs that AMD are building. But of course, if I have an FX processor or I have a Ryzen processor, I can still install Windows or Linux or whatever on it, because they are following the same basic instruction set architecture. And it's the same with ARM. We've had Cortex-A53, Cortex-A55, Cortex-A73, Cortex-A76, and these again are all microarchitectures design. So when you're designing a processor, you start with the ISA, whether it's Intel's ISA or ARM's ISA or RISC-V's ISA, and then you need to build a chip that actually can run programs that follow that ISA. And that, as you can see here, all these companies for years and years and years make different processors, and it costs a lot of money, and it takes a lot of engineers to build these things so they are efficient and they are fast and they do everything that we want them to do. And then once you've got the CPU design, there's a whole load more of other stuff that has to go into a processor. So interconnects here is talking about how the processors might talk to other things on the chip. And so you have to have these ways of interconnecting them. These often include caching and memory controllers and the buses, and these all need to work in kind of together so that you can get an efficient transfer of data across the chip. And then of course, if you include things like a GPU or a DSP or an ISP or media decoding and encoding, these all need to talk to the CPU over these controllers and buses and interconnects, and they need to do it efficiently, and they need to do it in a power efficient way. Okay, and none of this is covered by RISC-V. None of it. So when you buy an APU, for example, from AMD with the GPU and the CPU on the same chip. It will have internets and buses and caching controllers. It has the GPU on it. It probably has some media decoding stuff on it. None of that is covered by RISC-V. It's the same when you buy an SoC from Qualcomm. If you buy a smartphone with an SoC from Samsung, it's got all these things in it, and none of that is covered by RISC-V. So don't think that RISC-V is kind of this thing that covers everything and magically you can get a processor out the other end of it. There's a load of stuff that goes on once you go outside of the basic CPU. Now, with open source software, the level of entry is really easy. Basically, if I have even the cheapest second-hand PC, if I have even a moderate internet connection, I can start compiling programs, whether it's for Linux, whether it's for Windows, whether it's for whatever my favorite operating system, using whatever tools I've got available, and I can upload my project to the internet. I can submit patches, I can submit changes to other projects, and actually it's pretty easy. I sit at my desk and I just do it, and within a few, even a quick change, within a few moments I can have a change published up to the internet. But hardware isn't like that. Hardware, you need millions of dollars if you want to start producing chips, at 7 nanometers, even at 14 nanometers. Now, there are ways of getting chips made relatively cheaply, and we'll talk more about that in a minute. But for microcontrollers or for very small chips, but if you want to do something like what Intel do or what ARM do or what Samsung are making, you're going to need a lot of money to start making those chips. So just because RISC-V itself is an open source architecture, that doesn't mean you're going to find some person sitting at their desk hacking out the next version of the world's leading RISC-V processor. It's not the same dynamic as open source software. Changes and designs can't be tested simply. Now, FPGAs do help that situation. Okay, so if you want to make a simple chip, if you want to make a simple CPU, then doing it on an FPGA works. Now, I've got an FPGA board here that I play around with. I think it cost me about $60. Okay, so you can actually get into FPGA design relatively cheaply, okay, but you're not going to be able to run the equivalent of an 6th generation i3 Intel chip or a Cortex-A76 on an FPGA. Okay, they're not competitive enough. They're not enough for competitive processor designs. Okay, they don't give you enough when you start dealing with a 2.3 gigahertz octa-core processor. You're not going to be able to do that in FPGA. So there's going to have to be a manufacturing process at some point where a lot of money is spent in making a chip. This is why you're finding it's companies like Western Digital and Nvidia and others that are getting onto the RISC-V bandwagon because they've got that money. It's not some guy from the University of who knows where starting to make chips because that's what he wants to do. Very different situation, to a different dynamic than what we have with open source software. Now, once you physically got your chip, of course, you then need to run software, and of course, hardware without software is useless. Now, this is one major advantage of RISC-V, is that once you do get your chip, even if it's a simple chip, even if it's running on FPGA, okay, then you've got things like compilers and debuggers. You can run Linux, you can run FreeRTOS, okay, and anything that people develop, okay, for a RISC-V system should be able to run on your chip as long as there is some kind of compliance going on. We'll talk about compliance in a minute. Now, of course, there is a huge ecosystem from just running Linux. If you think about Android, for example, you've got Google's part of it, you've got Google Play services, you've got the App Store, but you've got the apps that run at the end. So there is going to be an advantage to using an ISO that's already supported. Now, at the moment, Android isn't officially supported on RISC-V. If it ever was supported on RISC-V, then that would mean that that whole ecosystem now opens itself up to anybody that has designed a RISC-V chip. So that's really good. There are other things that we need to think about, particularly in today's environment, things like virtualization and containers. This isn't something we're really hearing about on RISC-V at the moment. Definitely got it on ARM, definitely got it on Intel, definitely got it on AMD, but not something we're seeing yet on RISC-V. So, but the advantage of following this ISA is that you do get kind of the software part for free. Now, by default, only the core instruction set architecture must be implemented for someone to say, I've got a RISC-V chip. But there are lots of extensions, and these extensions are actually quite interesting because even things like floating point or bit level manipulation are actually extensions to the core instruction set architecture. So many of these extensions are not ratified yet. Some of them are, but some of them are not. So there is this kind of grey area at the moment. This will change absolutely, where you could build a processor that does extra things like floating point or bit manipulation, or in fact, you've got a little list here I've made, these kind of DSP instructions, or these kind of SIMD instructions, or virtualization or cryptography. These are kind of extensions that people are having to add on to the RISC-V processor to be able to get it to work. So at the moment, if you have a RISC-V processor, it might not necessarily do all the things you want it to do. And that leads us to the problem of what about non-standard extensions? What happens if someone creates an extension that will do something really snazzy, something really, really important to do with, DSPs or whatever, but actually it's not a standard extension? Well, we'll talk more about that in a moment. Okay, so that was my second video on the RISC-V processor. I hope you're enjoying this series so far. 2 more videos to go. The next one is about the problems of compliance and the possibilities of forking the RISC-V project. And then the last video will be about my predictions about what will happen in the future. So please do stick around, and I'll see you in the next one.